Welcome back. Today we will discuss variance and covariance. So, the variance of a random variable x is defined as the expected squared variation around the expected value, all right. So, it is assumed that expectation of x exists, right. Suppose suppose expected x exists and it is finite, right, and then you define the variance of the random variable x as the expected square variation around the mean, around the expected value, okay, and it is denoted by sigma x squared, okay, and sigma x. So, sigma x square is variance and sigma x is called standard deviation. So, standard deviation is used more in statistics and variance is used more in probability. Okay. So, you consider x minus expectation of, this is just a number, right, if it is finite, this is just a number if this is finite, x by this is x minus a constant whole squared. So, that is a random variable whose expectation you take. So, since this is a non negative random variable, its expectation is always well defined, correct. So, variance is, so as long as expectation of x is finite, this variance is always well defined. It might be infinity, right, but it is always well defined. There will be no problem of x plus x minus and both being infinity, that is because this what is inside is a non negative random variable. So, this is always well defined, could be real number, it could be plus infinity, okay. So, this intuitively this variance gives you a measure of how much the random variable deviates from its expected value, okay. So, a large value of the variance means that the random variable takes values which are spread around the expected value considerably, and if the variance is small, it means that the random variable takes values roughly close to the expected value with higher probability, right. That is roughly, very loosely speaking, that is what it implies, that is what it signifies, right, this variance. So, clearly this variance is non negative, right, that must be clear, this must be clear just by the definition, correct. Now, can the variance be 0? Yes, if x is almost surely constant, if x is a constant with probability 1, then its expected value is equal to that constant and therefore, the variance will be 0, okay. In fact, the converse is also true. If the variance of a random variable is 0, then you can state that the random variable is constant with probability 1, okay. Variance of x is equal to 0 if and only if x is almost surely constant. See, if x is almost surely, the if part is easy, right. If x is almost surely constant, then the random variable, let us say x is equal to some constant c with probability 1, then expected x will also be equal to c. So, then is clearly you are just taking expectation of 0 squared, right. Then you will have, so with probability 1 this difference will be 0. So, you will have variance is equal to 0, right. So, if part is easy. So, if part is easy. So, let us do the only if part. So, the only if if expectation of x minus expectation of x whole squared equal to 0, then integral x minus expectation of x correct. This is what it means, right. This is the definition of this expectation, right. Now, you have to invoke a property of the integrals saying that if you have a non-negative function whose integral is 0, then the function is 0 mu almost everywhere. Now, that mu is simply p, right. So, this is so using property number, can you tell me what property number is it in the properties of integrals, right. So, using property, so using property whatever, right. So, you tell me what property. So, we note that, we see that x minus expectation of x whole square equal to 0 with probability 1, which means x is equal. So, on a set of probability 1, this x minus expectation of x whole square is 0, which means x minus expectation of x is 0 with probability 1, right. So, yeah, you fill up this property, I do not know which property number it was, 6, okay, good, 6. Okay, so that settles one thing, right. So, variance is always non-negative and it is 0 if and only if the random variable is almost surely constant. Okay. So, the expression for variance which is easier to compute can be obtained by simply expanding out the squared. Okay. This is something you may be familiar with. So, a sigma x squared you can write it as expectation of, just expand this guy out, you get x squared plus expectation of x the whole squared, right, minus 2 x expectation of x, right. I am just writing a minus b whole squared as a square plus b square minus 2 a b. Now, I will invoke linearity of expectation. Okay. So, I have 1, 2, 3 random variables. This guy is just a constant, it is not even a random variable, right. This is just a constant. So, I will have expectation of x squared plus expectation of x squared minus, so this guy is a constant again, it will come out of the expectation, right. So, you will get expectation of x squared plus expectation of x the whole squared minus 2 expectation of x times expectation of x, right. So, I am bringing this. So, you think of this as a constant and you bring it out of expectation, right, that is a property of expectation also. So, this is equal to expectation of x squared minus expectation of x squared. Okay. All right. So, that is often easier to compute rather than evaluate. So, if you are given some distribution, some exponential or something like that, this is a little tedious to apply, this is easier to apply. You first compute the expectation of x, compute the expectation of x squared separately, and then subtract the expectation of x squared and expectation of x the whole squared. So, since variance is always non negative, you know that. So, this guy is non negative, right. So, that means for every random variable the expectation of x squared is always bigger than or equal to the square of the expectation. Okay. So, you take square the random variable first and take expectations, you will get something that is bigger than or equal to taking the expectation and squaring it. Okay. And in fact, if expectation of x square equals expectation of x the whole squared, then you can conclude that x is constant almost surely. Okay. In fact, did you do Jensen's inequality in your homework? It's in the homework that is coming up, right. So, if you have a convex function, if you might have seen your homework, if you have a convex function. So, roughly speaking convex functions look like that, right. There is a more proper definition in your homework. So, if you take any convex function g of x, expectation of g of x is always bigger than or equal to g of expectation of x, and in this case the function is simply the square function is convex, right. So, this is bigger than or equal to that. Okay. So, this Jensen's inequality is a very important inequality, you will do that in your homework. Okay. Okay, so any questions so far? Fairly straightforward stuff, right. So, you probably know this already. So, let us look at some examples. So, if you have a Bernoulli random variable x is equal to 1 with probability p and 0 with probability 1 minus p, in this case you will have expectation of x squared is simply 1 times. So, this is p, then expectation of x is also equal to p, right. So, variance of x will be p times 1 minus p. Okay. So, there is an example in your textbook where x is Poisson. In your notes you have this example, e power minus lambda power k over factorial k for k greater than or equal to 0, right. K in this case expected x squared. So, expected x first of all is equal to sum over. So, it is simply sum over k equals 0 to infinity k times e power minus lambda power k by k factorial. So, what you will get? So, you will get lambda. Okay. So, what will happen is that the 0 term will be 0, and for every k, for k greater than or equal to 1, you will have k and k factorial will cancel, will give you k minus 1 factorial. You pull a lambda out, you will get get 1 again. So, you will get this will be equal to lambda. Okay. You can just do the summation, and for this for expected x squared which is sometimes referred to as the second moment, expected x squared, for that will be sum over k squared e power minus lambda power k by k factorial, k equals 0 to infinity. You can do some manipulation now. Okay, so what this boils down to is you can write k squared as so you can do some manipulation here. Let me write it this way: k equals 0 term is 0 obviously, k equals 1 through infinity. So, you can write it as k I think I have to do something like that if I remember correctly, k squared minus k plus k times, I think this is what works. Okay. So, this is as so this guy will give you lambda, right, this part will give you lambda, right. So, if you take that, so k square minus k will cancel with that to give you k minus 2 factorial, right. So, that will be sum over k equals 2 to infinity lambda squared e power minus lambda to the k minus 2 over k minus 2 factorial. Okay. So, I am just considering that this bit, right, plus sum over k equals 1 through infinity lambda e power minus. So, this term you will get lambda e power minus lambda power k by lambda power k minus 1 by k minus 1 factorial. Okay. So, this will again, so this will be lambda squared plus lambda, all right. So, variance sigma square x will be lambda squared plus lambda minus lambda squared, right. So, the variance is also equal to lambda. Okay. So, for the Poisson random variable, both expected value and variance are equal to lambda. Let us do a couple of continuous random variables as examples. So, if you have x is uniform in a b, okay. In this case you can, so your expected x will be equal to a plus b over 2, okay. You can show that, and expected x squared will be equal to right. So, this will be b cubed minus a cubed over 3 b minus a, okay. And that will simplify further actually. this is, I think this is equal to a squared plus a b plus b square over 3, right. And then you compute sigma x squared as a squared plus a b plus b square over 3 minus this whole squared, right, which will be a squared plus 2 a b plus b square over 4, right. So, that will be 4 a b 6 a b. So, this should be, so this should finally come to b minus a squared over 12, okay, if you just rearrange this, guys. So, the variance of a uniform random variable is the width of the interval squared over 12. Okay. So, in the case of an exponential, you can show that, so we know that expectation of x is 1 over mu, we already derived that. You can show that expectation of x squared is equal to, this also we showed, I think in some other time, 2 over mu squared. So, variance will be this minus square of that, which will be 1 over mu squared. So, in all this you see, so if your uniform random variable here is spread over a wide interval, the variance will be bigger, right. Similarly, if your exponential is, if your parameter mu is, so it is this, the PDF looks like this, right. If you plot f x against x, it looks like that with value 1 over mu. So, if your mu is very small, yeah, when your mu is very small, your this curve is very spread over, it is like very flat, right. So, the variance is big, and if mu is large, this distribution is very peaky around 0 and your variance is smaller, right. So, that intuition keeps coming through. Then finally, in the case of the Gaussian, so remember we defined, so we had n mu, what is this the Gaussian density n mu sigma squared, right. Sigma square root of 2 pi e power minus x minus mu squared over 2 sigma squared for, so this is for all x in R. Here actually this mu is the expected value and sigma square is the variance. Okay. You can actually do the integral, it is a dirty integral, it is not it's easy to compute, but you can do it. If you compute integral x f x dx, you will get mu, and if you compute the variance, you will get sigma squared. Okay. So, in fact, so this Gaussian distribution is parameterized by mean mu and variance sigma squared, okay. So, which is why we called it sigma squared in the first place, right. So, this looks like, so I plotted this earlier. So, it is a distribution that is, it looks like that, right. So, it is centered at mu, it is a symmetric distribution, it is symmetric around mu, the expected value, and it goes down like e power minus x squared, x minus mu whole squared, and it goes down. So, if your sigma squared is if your sigma squared is small, then you have the value at x is equal to mu will be quite high, because there is a 1 by sigma term here, right. And the rate, if your sigma is small, it also goes down very quickly, right, because your there is in this e power minus, if this was small, then this whole exponent would be very big, e power minus all that will be very small, right. So, when sigma is very small, you have a very highly peaky distribution which falls down very quickly, right. And on the other hand, if your sigma is very large, you will have something that is not very tall and then is very broad, right, very broad spread out Gaussian. Again you see that the variance being small means the distribution is very concentrated around the expected value. Okay. So, this integral I will not do, okay. It is a pretty, there is slightly dirty integral, you have to do integration by parts and use some standard integral, right. Okay. So, any questions? So, could it be that the variance of a random variable is infinite while the mean is the expected value is finite? So, if the expected value is infinite, so then variance is not even defined. So, we only talk about variance if you have expected x finite, right, otherwise this formula would not make sense, right. So, if so is there a case, my question is there a case where the expected value is so the expected value is finite, but the variance is not. Variance is always defined, it could be plus, it could be either some real number or plus infinity, right. Variance is, so it is a non negative random variable, right. So, it is defined. So, is there a possibility of having expected value of x is equal to some finite number and variance is equal to infinity? Can somebody give me an example? So, okay, first, okay, you know an example where the mean is plus infinity, expected value equal to plus infinity, one sided Cauchy, right. Cauchy itself does not have a mean, right, expected value is undefined. So, one sided Cauchy has an infinite expected value, therefore, the variance is, I mean you cannot, if the mean is infinite, you can clearly say that variance is also infinite, but I am saying the opposite. Is the mean finite and variance infinite, is it possible? Erlang. So, what does the Erlang look like? No, see the Erlang looks like, basically in essence it looks like x power n minus 1 e power minus x, alright. So, the Erlang has all moments, all power moments are finite, okay. So, why is, so think about why is the Cauchy, the one sided Cauchy you said has an infinite expected value, right. Why is that? Because it goes down as 1 over x squared, right. So, when you hit it with an x, you get some infinite integral, right. Now, I am asking you if it is possible to keep the expected value finite and have the variance infinite. So, what would you do? You do, yeah, if you consider a distribution that goes down as 1 over x cubed, right, or even a discrete random variable which is like 1 over k cubed for k greater than or equal to 1, you have to normalize appropriately, of course. Then you will have a situation where the expected value is finite, but expected x square will be infinite, right. So, you can therefore cook up an example with finite expected value, but infinite variance, okay. All right, any questions? So, this covariance is a number that measures how two variables, random variables x and y jointly vary in some sense, all right. So, this variance is defined only for one random variable x, right, and it captures how much of a variation around the expected value the random variable has. This covariance is defined for two random variables x and y, and it captures this. So, definition, the covariance of random variables x and y is defined as expectation of x minus expectation of x, y minus expectation of y. Okay. And if you simplify that, you get expectation of x y minus expectation of x times expectation of y. Assuming, see, this definition is assuming that all these are meaningful, right. We have to first, this is makes sense only if expectation of x y has a meaning, and you should not have a situation where this is infinity and one of these guys is also infinity, right. You should not, I mean, all that in all those cases it is not defined, right. If this is infinity and that is infinity, right, you cannot define the covariance. So, this is defined subject to everything being well defined, the expression itself being well defined. Okay. Okay. So, this is the covariance. So, this is again, so this expression is more useful in computing covariance, whereas this expression gives you better intuition on what the covariance is actually doing. Okay. So, let us say that x and y are random variables, of course, they are on the same probability space. So, suppose that x and y have the tendency, for the time being, let us assume that whenever x is bigger than the expected value, suppose that y has the tendency to be smaller than the expected value, right. Then you will have a term that is negative, right, and if x and y tend to be both on the same side of the expectation with a greater probability, either both greater or than the expected value or both smaller than the expected value, then you will have a positive value for the covariance, right. So, in that sense it captures the joint, the expected joint variation in some sense, correct. If I tell you that x is, if whenever x is takes a large value bigger than the mean, then y is also likely to take a large value, right, greater than its mean, then you will have a positive covariance, right, and similarly in the negative case. Okay. So, that is covariance. Any questions? Definition: x and y are said to be uncorrelated if covariance of x y equal to 0, i.e. expectation of x y equal to expectation of x times expectation of y. So, if the covariance turns out to be 0, okay, so this could turn out to be 0, right. In such a case x and y are said to be uncorrelated. Okay. It is a new term you are learning. Okay. So, x and y are said to be uncorrelated if covariance is 0 or x and expectation of x y is equal to expectation of x times expectation of y. Okay. Now, theorem, this is an important theorem. If x and y are independent random variables, they are uncorrelated. So, this is an important theorem. Okay. So, independent random variables are always uncorrelated. So, if you take two independent random variables x and y, expectation of x y will always be equal to expectation of x times expectation of y. Okay. Now, so I will prove this theorem. Okay, it is a very important theorem and it is a somewhat non-trivial proof. So, the one thing I want to remark before that is that the converse is not true. Okay. If two random variables are uncorrelated, it does not mean that they are independent. Okay. So, independence implies random variables are uncorrelated, but not the other way around. Okay. So, which is stronger independence or uncorrelatedness? Independence is stronger, right. Okay. So, remark, the converse is not true. So, can somebody tell me why the converse is not true? How will you prove that the converse is not true? So, how will you prove that two random variables uncorrelated does not imply that they are independent? That is what is given to you, right. You are given that they are uncorrelated, you have to show that it does not imply independence.
Even though it separates, the condition is met.
Some
Constant. So, you want to take constant random variables. So, then what? So, both constant random variables. So, if two random variables are both constant, the sigma algebras they generate are simply omega and phi, right. So, are they independent sigma algebras? They are, right. So, they are also independent, that is a very trivial case. So, two constant random variables are independent right. So, that is not an example. Same, then they will not be, if x and y are equal, by the way, you get variance, right. So, you have to cook up a, it is not entirely trivial, right, but there are some easy examples to show that. So, consider, so there are many examples you can cook up, but consider x uniform in -1 to 1. Okay. So, uniform random variable in -1 to 1. We can show that x and x square are dependent, but uncorrelated. Okay, so, this is, if you produce one example it is enough, right. So, I am just considering a random variable x which is uniform in -1 through 1 and then say y equal to x squared. Okay. So, in that case I mean I think you will be able to very easily show that x and x square are not, when you nobody will believe that x and x square are independent, right. So, you can actually explicitly show that if you want you can compute the you compute the joint distribution of y and x, right, and you will very trivially you can show that they are dependent. However, they are uncorrelated, right, because so you say y equal to x squared, covariance of x comma y is equal to expectation of x y minus expectation of x times expectation of y, which is equal to expectation of x cubed minus expectation of x times expectation of x squared, right. You can see expectation of x is 0, right. So, this term is definitely 0 and x being symmetric around minus 1 and 1, x cube will also have a, you can prove that x cube also has 0, expect this term is also 0, right. After all, this expectation x cube is simply integral of x cubed half dx, is not it, from minus 1 through 1. This is expectation of x cubed, correct, that is clearly 0. So, this is also 0, right. So, x and x squared in this case are uncorrelated, but dependent random variables. Okay. Okay, so, I think I do not have the time to complete this proof, or maybe I will just start it. Okay. So, I want to well I am going to prove this, right. I have proven that the converse is not true, I have to prove the theorem now, right. Proof of the theorem. So, I have to prove that if x and y are independent they are uncorrelated. How do you prove it? PDF, but who says x and y has a PDF, right. Expectation of x y is integral x y dp, right. Correct. Again, right. So, this is a theorem you would have proved separately for discrete random variables, proved separately for jointly continuous random variables, and then blindly accepted that it is generally true, right. Now, you are going to prove a general theorem, which is why I said it is a non trivial theorem, right. So, if you have density, so if x and y had a joint density, you would just evaluate those two things separately and show that oh it holds, right. But x and y may not have a joint density, they need not have a PMF, right. They may not be discrete, one of them may be some singular, another may be some mixture, right. Even in that case this holds. Okay. So, how will you prove that? By now you should know, right. How do you prove anything in integration? Start with simple functions, right. So, suppose x and y are independent simple random variables. So, I have x has a representation sum over a I of a I does this representation, and y has sum over I equals j equals, let us say j equals 1 through m b j I of b j. Okay. In this case, can you prove it? So, in this case, so x y, right, x y will be what? Sum over x y will also be simple, right. It will be sum over I equals 1 through n, j equals 1 through m, a I b j, indicator A I intersection B j, correct. Suppose I mean these are let us say in canonical representations for the sake of to fix ideas. So, this is your expectation of, so this is your x y random variable itself. So, expectation of x y would be, so this is a simple function, right. So, this will be I equals 1 through n, j equals 1 through m, A I B j probability of A I intersection B j. So, now what can you say? Now is the key step. See, after all, A I, see what is A I, right? A I is the event that x is equal to, correct, and B j is the event that, correct, fine. So, now this A I and B j are independent events. Why? X and y are independent random variables. So, this will product out, correct. So, this by independence, so by looking at this you can say that these two are independent events, right. So, this will be equal to A I B j P A I times P B j, right. So, now the A sum and the B sum come out, right. So, you can take the I summation, this only has i's and these two have the j's. So, now it products out easily, right, and what you have is the expectation of x times expectation of y, right. So, this you can show, okay. Yeah, expectation of x times expectation of y. So, we have shown it for simple random variables. So, we will complete the proof next class. Now, what do you have to do now? Approximate x from below using simple functions. Then you would have proved it for non-negative random variables, and then finally, you have to do x plus x minus y plus y minus, then get the result, right. Okay. So, tomorrow we are meeting at noon, okay. There is a change in the timetable, isn't it. So, tomorrow there is an exam. So, 12 o'clock is the class right here.